On the definition of exponential function, when we're talking about exponential function, we're talking about something like b to power x. B is a number which is positive, b cannot be equal to 1. Then this function with changes in power or in exponent x or variable on the exponent is called exponential function. Remember the graph of b to the x. The graph of b to the x depends on the behavior of b. If b is more than 1, then the graph is increasing. But if b is bounded between 0 and 1, the graph is decreasing. When b is more than 1, as you can see, f is an increasing exponential function. Sometimes we call it exponential growth function. And when b is bounded between 0 and 1, like a half, a third, or any number in that sort, f is called decreasing exponential function, or sometimes we call it exponential decay. The domain of the function is negative infinity to positive infinity, and the range, as you can see, is between 0 to positive infinity. The line y equals to 0 is the horizontal asymptote for this function. The function passes through the point 0 and 1 because f at 0 is equal to b to power 0 or 1. So this is a little bit of algebra. Now, we're going to define hyperbolic functions. Hyperbolic sine of x, or you write it as sine hyperbolic hx, is defined as e to power x minus e to power minus x divided by 2. The graph can be visualized this way. This is the graph of hyperbolic sine. With the same argument, we can define hyperbolic cosine of x. So again, these are some new functions that are related to exponential functions, and they have specific behaviors. They are useful in rate of change. They're useful in taking the integral. Hyperbolic cosine of x is e to x plus e to power minus x divided by 2. The next hyperbolic function that we're going to define are tangent and cotangent. It's good to review the graph of these types of functions and try to feel comfortable about their behavior. So for example, for hyperbolic sine, the behavior of the function is like this. And for hyperbolic cosine, you see it's very similar to a parabola of some sort. Hyperbolic tangent. Hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine, which is e to power x minus e to power minus x divided by e to the x plus e to power minus x. Hyperbolic cotangent is hyperbolic cosine divided by hyperbolic sine, or e to power x plus e to power minus x divided by e to power x minus e to power minus x. The graph behaves like this. For hyperbolic tangent, this is the behavior of the function that you have. And for hyperbolic cotangent, as you can see, the graph is divided up into 2 pieces. Let us introduce hyperbolic secant. Hyperbolic secant, as you remember, is 1 over hyperbolic cosine, which is 2, divided by e to the x plus e to power minus x. The behavior of the graph of 1 over hyperbolic cosine or hyperbolic secant is like this. Next, hyperbolic cosecant, which is defined as 1 over hyperbolic sine, or 2 divided by e to the x minus e to power minus x. Very good. It's very similar to reciprocal function. Now we're interested in finding the derivative and then the integral of these types of functions. d dx of hyperbolic sine of x is the derivative of e to the x minus e to power minus x divided by 2, which in turn is e to the x plus e to power minus x divided by 2. And as you know, it's the definition of hyperbolic cosine. So the derivative of hyperbolic sine is the same as hyperbolic cosine. Now, if we take the derivative of hyperbolic cosine, what is the expectation? Let's see. It's equal to the derivative of e to the x plus e to power minus x divided by 2, which is e to the x minus e to power minus x divided by 2. And as you remember, this is the definition of hyperbolic sine. So the derivative of hyperbolic sine is hyperbolic cosine, and the derivative of hyperbolic cosine is hyperbolic sine. There is no negative sign involved. So let's continue our discussion on the derivatives. So far, we saw that the derivative of hyperbolic sine is hyperbolic cosine. And we also saw that the derivative of hyperbolic cosine is hyperbolic sine. What if you take the derivative of hyperbolic tangent? It is equal to hyperbolic secant squared. And if you take the derivative of cosecant hyperbolic function, you get negative hyperbolic cosecant times hyperbolic cotangent. The derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent. And finally, the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. Remember that we're going to use these and find the integral. In integral formulas, since the derivative of hyperbolic cosine is hyperbolic sine, so we expect the integral of hyperbolic sine to be hyperbolic cosine. Don't forget to add the integration constant as well. Since the derivative of hyperbolic sine is hyperbolic cosine, so the integral of hyperbolic cosine is hyperbolic sine plus c. Since the derivative of hyperbolic tangent is hyperbolic secant squared, so the integral of hyperbolic secant squared is hyperbolic tangent plus c. Since the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared, so the integral of hyperbolic cosecant squared is negative hyperbolic cotangent plus c. Number 5, since the derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent, so if you take the integral of hyperbolic secant multiplied by hyperbolic tangent, it is negative hyperbolic secant plus c. And finally, since the derivative of hyperbolic cosecant is negative hyperbolic cosecant times hyperbolic cotangent, we expect the integral of hyperbolic cosecant times hyperbolic cotangent to be negative hyperbolic cosecant plus c. The next topic is inverse hyperbolic functions.